The purpose of this talk is to present a communication complexity task where the model of quantum simultaneity without any additional resources qualitatively outperforms the model of classical interactivity. Let us start by introducing the models. The interactive or two-way setting goes as follows. In the beginning, Alice receives X, Bob receives Y. These are two parts of the input. After that, they speak, so back and forth they exchange messages for as long as they wish. At some point, they decide that they are ready to answer, at which point Bob outputs the answer, which must be a correct answer with respect to the received input pair x, y. Another setup that interests us today is called simultaneous message passing, or SMP. Note first of all that here, unlike the previous case, we have three participants. We have Alice, we have referee, and we have Bob. The communication protocol goes as follows. In the beginning, as before, Alice receives X, Bob receives Y. The communication stage here is very different from what we've seen before because there is no interaction between players. Only two messages are allowed to occur. One message goes from Alice to the referee, another message goes from Bob to the referee. Given the values, the content of those two messages, the referee has to produce an answer. As before, the answer must be correct with respect to the received input pair x, y. And here, of course, we can see right away that the players or the model is much more restricted, much more limited, because there is no interaction, and also the party who has to produce the answer, the referee, does not receive, so to say, for free any portion of input. Because before, when in the two-way case, when Bob was answering, Bob knew the value of y. Here, the referee knows nothing a priori, and only knowledge that is available to the referee in order to produce her answer here. This is the knowledge received from the messages sent by the two major players, Alice and Bob. It may be instructive to put the two models that we have just defined side by side. We can see right away that indeed the first model, the interactive, the two-way, it gives our players much more flexibility, it gives them more power. And indeed, the second model is much more restricted. Schematically, we can see here that the messages, the way the messages go, are much more. The messages are much more limited. There is another possibility for defining the ways of interaction between the players in the case of two-party communication complexity. Namely, we can define so-called one-way communication. Probably many of you are familiar with that setup. For today's talk, we don't need that, but we can, those of us who are familiar with that setting can keep in mind that that is an intermediate setting, which is stronger than simultaneous message passing, but weaker than interactive. So far, we have seen several layouts or topologies of communication models. Now let us define the complexity. First of all, we will be dealing today with two types of communication protocols. So some protocols will be randomized. Other protocols will be quantum. In particular, we will not be interested in deterministic protocols. So any classical protocol that we will be dealing with or considering today is allowed to use randomness. The cost or complexity of a protocol in a given model is the total number of bits or qubits, if the protocol is quantum, that all its participants send. And here it is actually without loss of generality, but just to be specific, here we're considering the worst case. So the cost of a protocol is the highest possible total number of bits or qubits being sent. A communication protocol is efficient, or we view it as an efficient, if its complexity is at most polylogarithmic in the input length. This makes sense, this notion of efficiency, in the context of communication complexity. One of the most obvious reasons is that if we consider protocols of complexity linear in the input lengths, then in most reasonable models, protocols would be all-powerful, because once the participant, the party who is answering, is able to know all the input, then he can answer any question. So any problem, a communication complexity problem, has complexity at most linear. Usually we want exponential gap between the notions of efficient and inefficient in the context of complexity theory. That's why here by efficient we mean polylogarithmic. The complexity of a problem in a given communication model is naturally the minimum complexity of a protocol that solves this problem in that model. Sometimes we will we'll use the notion of communication complexity class, by which we will mean the family of all problems that have an efficient, that is polylogarithmic, protocol in the given model. Now that we have defined the main types of communication complexity models that will interest us today, let us briefly have a look at several types of communication complexity problems. The types that are of interest to us are three: total functions, partial functions, and relations. The definition is obvious. Recall that our problems all of them are bipartite. There are two players, each of them receives his portion of input. In the case of total function, the space of allowed input pairs is a product set, and for every possible pair from that product set, there is exactly one correct answer. Partial function, it's also a function, which means for every possible input value there is exactly one correct answer, but the set of allowed inputs does not have to be a product set. In other words, there are some pairs of values for x and values for y, such that let's say x0 by itself can show up as input to Alice in some situations. Y0 by itself can show up as input for Bob in some situations, but together they never show up. X0, Y0 are guaranteed not to be given as actual input to our players. And third type is a relation, which essentially means that the number of correct answers can be larger than one. There can be any number of correct answers for a fixed input pair. This separation is this division into types of communication problems is quite crucial because there are some known cases where a quantum communication complexity class is stronger than a classical, or let's say quantum communication complexity model is stronger than some classical model, but it's known to be stronger only for some relational problems, while it is also known that for any functional, either total or partial problem, the two classes are equal. So in other words, qualitative superiority of the quantum class can exhibit itself only with respect to a relation, but not with respect to a function. Speaking of the distinction between partial functions and total functions, there are quite a few pairs of classes where it is known how to separate the two classes via partial function. And it is conjectured that such separation is not possible via a total function. Later we will see that in the context of quantum simultaneous message passing, this hierarchy of three possible problem types, it seems to be especially interesting and especially relevant. Communication complexity is probably one of the most interesting setups among the currently studied theoretical models of computation. And the main reason for that is that the model the setup is at the same time strong enough to already allow some interesting, arguably non-trivial protocols, non-trivial algorithms for solving some problems. And at the same time, the setup is still within the reach of our analytical techniques. We're still able, for some problems and for some models, to show strong, often tight, lower bounds on the complexity of those problems. There is a number of known results that demonstrate qualitative superiority of quantum communication over classical communication. By our definition of efficiency, if some problem has an efficient solution in one model but not in the other, then the gap between the corresponding complexities must be at least superpolynomial. But actually, in all the examples that we mention next, the known separation is exponential. Please pay attention to the notation that is used to denote different models of communication complexity. In 1999, a partial function was shown that had an efficient solution in quantum two-way model, but had no efficient solution in the classical two-way model. In year 2001, a total function was demonstrated that had an efficient solution in the model of quantum SMP communication, but it had no efficient solution in the model of classical SMP communication. In the year 2016, an example was shown of a partial function that had an efficient solution in the model of quantum simultaneous message passing with shared entanglement. And this is a model very similar to the standard quantum SMP, but here the players are allowed to share some fixed quantum state before they receive the input, before the protocol starts, and then they can use this shared state in order to help themselves to solve the problem. A partial function had an efficient solution, efficient protocol in this model, quantum SMP with entanglement, but it had no efficient solution in the model of classical two-way communication. In year 2018, an example of a partial function, a different one, was shown that the function had an efficient solution in the model of quantum SMP without any shared resources, and the same problem had no efficient protocol in the model of classical SMP with shared randomness. Here, shared randomness means that when players need some random bits in order to decide how to proceed, those random bits are given for free to both the players, which means in particular the players can synchronize and can perform some mixed strategies. Pay attention that in that case the quantum model did not require, and as well as in all other cases, did not require shared randomness. Finally, today we will see a relation that has an efficient solution in the model of quantum SMP, and that is hard for the classical two-way model. Pay attention that this is the strongest possible indication of the quantum superiority in the two-party model, because the weakest quantum model can outperform the strongest classical model. However, the tool that we use in order to obtain this separation is the strongest available, namely a relational problem. Let us define the communication problem that will be used for our separation. We start by presenting the intuition behind the problem. The gap Hamming distance function is well known in the context of communication complexity. Here, the players who receive X and Y are essentially required to distinguish between two cases, either the distance between X and Y being at least n½ plus square root n, or the Hamming distance between X and Y being at most n½ minus minus square root n. You can see that this is a promise problem, as it is guaranteed that one of these two cases necessarily holds. The resulting communication complexity problem is known to have no efficient solution in classical two-way model. It's easy to see that it also has no efficient solution in the quantum SMP model. So let's try to make this problem simpler for quantum SMP while still preserving its hardness for R. If we manage to do that, we would get what we need for our separation. From the classical two-way hardness of this problem, we need the following intuitive fact, namely approximating the Hamming distance between two uniformly random n-bit strings with accuracy theta of square root n is hard for classical two-way. Let us fix at random a set of polynomially many permutations from the family of n-bit strings to itself. And the players now are required to produce a permutation from the set that we have fixed, such that this permutation maps the value of x to something that is slightly closer to y than expected, than in half. So you can see that morally this problem is similar to determining the Hamming distance between two uniform random strings. Indeed, this modification preserves the classical two-way hardness of the problem. On the other hand, it's not enough. The problem is not yet easy for the quantum SMP model. To simplify it even further, we let our players produce a list of log n permutations from the predefined set of polynomially many possibilities, such that on average the mappings, the images of x with respect to those log n produced permutations should be somewhat biased with respect to y. So this variation is very similar to the previous one, but intuitively it's less sharp. Instead of producing a single permutation that does the trick, now the players are allowed to produce a list of log n permutations such that on average this permutation should do the same trick. And this turns out to be enough. This modification makes the task easy for quantum SMP while preserving its classical two-way hardness. We are ready to define our communication problem, the gap Hamming relation. Let tau sub s be the standard Boolean Fourier basis for functions over log n bits. Every such tau sub s is a function from log n bits to plus minus 1, therefore it can also be viewed as an n-bit vector. For every j between 1 and n, let sigma sub j be the j's cyclic shift of an n-bit string. These two things together allow us to define our pseudo-random family of n-square allowed permutations of n-bit strings as follows. For every j and s, let rho sub js of x be the tau sub this n-bit string tau sub s bitwise XORed with x, then shifted by j bits. This is our mapping. We also define a function delta sub js of xy, which measures the Hamming weight, the Hamming distance between the raw image of x and y. You remember that this is something which is crucial for our idea of defining our communication problem. Now, next we define a predicate aleph of x and of two arguments x and y. The predicate is a little bit technical, and technicalities are currently not very important for us. What is important is the fact that aleph of x and y is satisfied almost always by a uniformly random pair of strings x and y. In other words, we can think about aleph as a typical property of a uniformly random pair of n-bit strings. So far we have defined the transformations rho, predicates functions delta, and a predicate aleph. Now let us define the relation itself. The input to it is a pair of n-bit strings, and the output is a sequence of log n pair of indices. we interpret each pair of indices as a pointer to one of the transformations rho, and we say that a sequence of such indices is a valid answer to the given input if at least half of the corresponding transformations map the value of x either somewhat close to the value of y or somewhat far from it. Of course, we have to formalize these notions of somewhat close and somewhat far in order to make the resulting problem easy for quantum SMP and hard for classical two-way. And here it is. Here is the technical definition. So you can see that the expectation of the value of every delta is exactly n-half, and we require that at least half of the deltas picked by the answer actually have value outside the interval of radius square root n-half around the expectation. You can see that the definition depends on Aleph. Again, we are going to ignore the technicalities of it now. What is important from the intuitive point of view is to remember that Aleph of x and y holds almost always for a uniform random pair of n-bit strings. Now that we have defined our communication problem GHR, let's see how a quantum SMP protocol tackles it. Let us keep in mind that the purpose of the protocol is to output a list of log n transformations from those rows that our construction allows, so that at least half of the corresponding values of delta would exhibit noticeable bias from the expectation n-half. The protocol goes as follows. First of all, we let Alice and Bob send to the referee log n qubits each that consist of, so to say, trivial fingerprints, Alice's input and Bob's input. Now define a set of quantum states UJS the way that is written here. Pay attention that this definition closely resembles the definition of the transformation rho sub JS that underlies our problem. Note that these states UJS are orthonormal, they form a basis, and therefore this is a complete projective measurement in terms of quantum mechanics. The referee can apply this measurement to the states, the pair of trivial fingerprints that he has received from the players. And then the probability of the outcome JS is actually proportional to this quantity. And pay attention that this quantity is the bias squared that we are interested in. So, in other words, this measurement applied to those two trivial fingerprints from the players, it favors those outcomes that correspond to the transformations that introduce some noticeable bias, and this is exactly what we want in order to solve our problem. So, if we repeat this whole procedure log n times, so both Alice and Bob send log n copies of their fingerprints, and referee measures each copy and outputs the result, this gives a quantum SMP protocol that solves the GHR problem, and the complexity of this protocol is O of log square n. Our lower bound on the complexity of the GHR in the classical two-way model is somewhat involved technically, but intuitively it follows the very standard route of analyzing large rectangles. Namely, we show that no large rectangle can be sufficiently biased towards one of the correct answers to the problem GHR. Let us conclude. We have just seen an example where the weakest quantum two-player model of communication, quantum SMP, is exponentially stronger than the strongest classical two-party model, classical two-way. The strongest known examples of the advantage of quantum SMP over a classical model, interestingly, strongly depends on the type of the problem that we allow. Namely, if we only consider total functions, then it's known that quantum SMP can outperform outperform classical SMP. If we allow partial functions, then quantum SMP can outperform classical SMP with shared randomness. Finally, we've just seen that if we allow relations, then quantum SMP can outperform classical two-way communication. It's very interesting to know whether these things are tied, or can some of those separations be improved. In particular, in connection to what we have just seen, can quantum SMP outperform classical two-way with respect to a partial function? Thank you.